So just to finish off our little note on Le Chatelier's principle, just a little bit of a review. Remember, Le Chatelier's principle guides us to get a quick qualitative understanding on what happens to an equilibrium when we apply a stress to it when it's at equilibrium. Add some reactant, it shifts to products. Add some product, it shifts back to the reactants. Take away some products, it shifts over to make some more product. We talked about the temperature changes. You have to analyze that depending on whether it's an endothermic or exothermic reaction, but all you have to do is imagine that an increase in temperature is an increase in energy available, which it is, and then it shifts accordingly. And then we talked about how you change the volume of a system, which then changes the pressure, which then squeezes, molecules together, moving it towards the side that has less molecules, or when you take the volume and you make it larger and you draw that pressure out, you shift it to the side then that has more molecules. Just to finish off, two factors that don't affect the equilibrium. And then how do we actually, laboratory-wise, in terms of experimentally, how do we actually add and remove product, or how do we actually, cause these shifts so that we can actually perform it in the lab? Okay, so adding a catalyst. We all know it lowers the activation energy. It makes the reaction speed up, but it makes both the forward and reverse reaction speed up at the same time. And the equilibrium may be achieved faster. It may get to equilibrium quicker, but the equilibrium position remains unchanged. So if you were to add a catalyst to a system that was at equilibrium, it wouldn't do anything. That dynamic equilibrium would now run a little faster, but it wouldn't affect that ratio of concentration of reactants to products. No effect. Okay, and one other factor that can affect it is adding an inert gas. It could be a noble gas. It can be just simply a non-reactive gas that doesn't react with the particular chemical reaction. And this is for a gaseous situation. Instead of maybe drawing a beaker, I should draw a balloon maybe. one can trick you up. Well, all right. Who's kidding who? I made many mistakes on this one. I always made the wrong conclusion because I always based it on pressure. I told you yesterday that if you change the volume of a system and you increase the pressure, you're effectively going to squeeze those molecules together and it's going to move to the side with the least number of gas molecules, right? Or if you drew it out and made the volume larger and made the pressure less, then you're going to move to the side that has more gas particles to kind of bring the pressure back up. And I'm always leery of telling students why this isn't correct, because some students you only hear half the story and then write it down as being correct. But in my mind, when I used to think this through, if you think about a gas, all right, and let's say those are the reacting particles. Those are the ones that are undergoing the equilibrium reaction. And I've already told you yesterday that the pressure is related to the concentration, or the pressure is inversely proportional to the volume, right? But that pressure is related to the concentration of the gas. Really, a concentration is like a number density, right? Number per unit volume. I used the term number density yesterday. Like a mass density is what you would call in science density, right? In grade 9 we say determine the density. But really we should be a little more specific. When we say density in grade 9, we really mean a mass density. Mass divided by volume, right? Because you know in geography you can have a population density, right? Which is essentially a number density, number of things per unit whatever, right? And so a pressure is actually a number density. It's how many particles are in a particular volume if we were to count them up, right? The number of moles of particles. Now if you add an ideal gas, so let's say we've got our syringe here now, and if we can do this without popping the balloon, right? Let's say that we could inject another gas, not an ideal gas, but another gas that isn't reactive. All right, so I add an inert gas. If you take a look at that picture, have I changed the number density of the reacting particles? If I'm just looking at the white dots and I'm ignoring the orangey, peachy dots, whatever color they are, have I changed the number density of those reacting particles? No. So I haven't changed the concentration of the reacting particles just by introducing another gas. Now last year I would have taught you about a law called Dalton's law of partial pressures. It states that a mixture of gases, the total pressure is equal to the sum of all the individual pressures. And maybe before we added that noble gas, that we had a certain pressure, right? And we'll just call that, say, P1. And then after we added the gas, we would have had a different pressure because we added some more, and that would be equal to the pressure of the reacting gases plus the pressure of the noble gas, right? And so our total pressure has gone up, but the partial pressure of the reacting gases hasn't changed. It means the number density stays the same. It means it doesn't do anything to the reaction, right? In a gas, really, the particles don't even realize the other particles are there. They're zinging around all on their own. What I did in my mind, I always thought of adding that gas as being an increase in pressure, and I analyzed it as such. I got it wrong every time. Now, I didn't really get it straight until I had to teach it. And then I started to think about what's going on here. Why am I getting this wrong every time? Oh, we're not changing the pressure of the reacting gases. We're changing the total pressure, but the pressure of that reacting gas stays the same. And therefore, the fraction stays the same in the equilibrium constant. It's still in equilibrium. It's not going to do anything. So adding a noble gas doesn't do anything. Okay, so now on to how we can actually change reactants and product concentrations so we can get to the experiment. And as you're writing that, I got to get a couple more of these drop trays. I think I need 2 more. Okay. So how can we practically change reactants and product concentrations in a laboratory? Well, for the sake of ease, we're going to be doing aqueous reactions because gaseous reactions involve very complex apparatus in order to move gas around and to get them into the places you want them to be. I've observed an apparatus, and I've observed a chemist doing some gas reactions, but it's a tricky thing to do. Obviously, we can't do it here. You need mountains of equipment almost. So obviously, we're going to be doing aqueous reactions, and one thing is we can use acid and base properties. So if we've got a reaction that contains either an acid on one side, you'll see the H pluses there, and you'll notice we're not really including what type of acid it is. We're just representing the fact that it's got H plus there on the one side. Then we can use a base to grab up some of that H plus, all right, and we can, lock it into some water molecules. And what that effectively will do here on this reaction is it'll bring the concentration of H plus down. And essentially we will have removed some reactant. And if we do such, we should predict that it will shift left, okay? Now, in our experiment today, we're going to be using very, very highly colored reactants and products. Now, in this case, calcium carbonate solid, that's like, marble chips. That's not that exciting. It's like little pieces of marble. And then carbon dioxide is a gas. But when we do ours, one side will be highly colored, like maybe red, and the other one will be maybe yellow. And then if you have a mixture of both, it would be like orange. And if we take this away and it shifts to the side that's red, then we should predict that our color of our reaction should shift to the red side, right? So we're going to be observing color shifts. That's the easiest way for us to see that, all right? So if you've got an H plus, you can add some base. I guess if you have some OH, by the same logic, you could add some acid to it and grab up the OH. So if you had some hydroxide as a reactant or a product. Another classic way in which we can remove reactant or product ions is by locking them up in a precipitate. Now, I'm not going to expect you to go to your solubility charts and track down a good substance to react with it, but you could, right? In an extension type lab, right? I could say to you, all right, we've got copper and we've got chloride. We want to shift this to the left. I either have to grab up the copper or I have to grab up the chloride. You could go to your solubility charts and find an ion that would cause the copper 2 to become a solid, or you could find an ion that would cause the chloride to become a solid. It turns out there's not very many of them that will cause chloride to come out of solution, but silver is definitely one of them. So if we react it with some silver nitrate, that's going to lock up the chloride, make it become a solid. It's going to settle out to the bottom as a precipitate, and then we want to look at what that transparent liquid looks like at the, that's sitting above that precipitate to determine whether it's shifted or not. I believe this may even be one of our reactions. I can't remember. Oh, I suppose I could take a look. We do have a copper reaction, but it isn't straight up like that one. But in this case, if I grab up some chlorides and this shifts to the left, then we should expect it to become a little more blue because it's going to move back to produce more chloride ions in the absence of the ones that were grabbed up by the silver. In this case, if I wanted to shift it the other way, I could add some hydrochloric acid. That's going to add a lot of chlorides to the situation. I could have added a solution of sodium chloride. Remember, sodium, what did we call sodium? Again, we're going to need these concepts in the future. We might as well think about it. Why is sodium a great ion to add to a solution if you don't want the sodium to affect anything? what did we call the sodium ion? What's that? Yeah, it's always a bystander. What did we call it? We had a term for that ion. Started with the letter S. It's a spectator ion, right? So we could have used sodium chloride here. That would have dumped some chloride into the solution, and the sodium would just, hang out and watch, because it doesn't participate in any of those things. But HCl would work. Now, if there was H's in there as well, that might cause some trouble, because now you'd be adding H, so you'd have to maybe pick something else. Okay, and when you're done that, you can, I guess, put that away, and you can get your lab sheet out. And I'm going to stop the recording here, and I'll move it to the top corner so you guys can finish writing at the bottom. But we'll